Okay, so today we'll be talking about convergence. So we'll talk particularly about like three different types of convergence. Okay, so three different types of convergence for random variables. Okay, so the first definition is we say that a sequence of random variables x1, x2, and so on converges to x in distribution if fn of x converges to f of x, and this is the probability that xn is less or equal than x to the probability that x is less or equal to x. Converging distribution if fn of x converges to f of x for every continuity point x of f of x. Okay, and we'll denote this by xn converges in distribution to x. Okay, so this is the first mode of convergence that we saw in a couple of classes before. Okay, so similarly, xn converges to x in probability if for every epsilon positive the probability that the absolute value of the difference xn minus x bigger than epsilon, okay, so this is an event, goes to 0 when n goes to infinity. Okay, so for every epsilon positive, we have this, for every epsilon positive, we know that the event, that the probability of this event that the xn differs from x from a positive constant epsilon goes to 0 for every epsilon positive, no matter how small it is. And then finally, we say that xn converges to x almost surely. Okay, and here notation we'll use probably xn converges with a p on top of x. Xn converges to x almost surely if here let's try to write it. If the event omega in omega such that xn of omega converges to x of omega, okay, as n to infinity, has probability 1. Okay, so almost sure convergence says that up to some specific values of omega, which some values of omega that we can actually discard, we have pointwise convergence of the value of xn to x. Okay, so but this happens for every this happens as n goes to infinity, and then okay, so what we're going to see is the relationships between these different definitions. The idea is that they are going in a bit of an increasing order. This is the weakest one, this is slightly harder, and this is harder. Okay, so usually when you have a sequence of random variables, they might converge in one of the settings but will not converge in the others. Okay, so let's look at examples. So examples. So let's say somewhat of a trivial example, let's say that xn is identically equal to the constant 1 over n, okay, so almost surely. So then xn converges to x, which is equal to 0, and the convergence is in distribution, in probability, and almost surely. Okay, what's another example? This one is a bit more non-trivial. Let's say that we have that xn is equal to x, which is a Bernoulli, or let's call it z, which is a Bernoulli variable with parameter 1/2. Then what we have is that xn clearly converges to z in distribution, in probability, and almost surely. Okay, but also we can consider x, which is equal to 1 minus z. Okay, so if we take a Bernoulli variable with parameter minus 1/2, and we take 1 minus c, this is still distributed as a Bernoulli variable with parameter 1/2. But now, okay, so in particular, therefore, xn converges in distribution to x. But, so xn is equal to z for every n, but then what we can see from here is that xn minus x, which is going to be equal to z minus 1 1 minus z is going to be 1 plus z beyond the point. So let's say take xn minus x. What we end up getting is 2z minus 1, which is always equals to 1, okay? Which implies that xn does not converge to x in probability. And clearly it also implies that xn does not converge almost surely to x. All right. All right. Okay, so now let's start with the implications. So what we are going to say is that convergence in probability implies convergence in distribution, and that almost sure convergence implies convergence in probability. Then in the exercise, I am pretty sure there is an example to show that the converses are not true. In this particular thing, we also show that there is a converse that is not true. Convergence in distribution does not actually imply convergence in probability. Okay, let's start with a theorem. Almost sure convergence imply convergence in probability. Which implies convergence in distribution. Okay, remark, the converses are all false. Okay, so let's start. Okay, so let's call this A, and let's call this B. Proof. Let's start with B. So V. So here we want to show that convergence in probability implies convergence in distribution. So let's look at the distribution for xn. So fn of x is equal to the probability that xn is less or equal than x. But now, by the law of total probability, we can decompose this as the probability that xn is less or equal than x intersection x is less or equal than x plus epsilon, plus the probability that xn is less or equal than x and capital X is bigger than x little x plus epsilon. But then this implies this is less or equal. So in particular, the first term is less or equal than the distribution function for x. So f of x at x plus epsilon plus the probability. Okay, so the point is that in this set, xn and x differ at least by epsilon. The probability that xn minus x is bigger than epsilon. Okay, so that's one of the inequalities. So in particular, this implies taking lim sub n to infinity, we have that the lim sub n to infinity of fn of x is less or equal, so in particular this goes to 0 when n goes to infinity, is less or equal than fx of x plus epsilon. And this is, here we have done it for arbitrary epsilon, so this is valid for every epsilon positive. Similarly, we can start by f of x minus epsilon, and this is going to be equal, if we do the same decomposition as we did here, the probability that x is less or equal than x minus epsilon, comma, the probability that xn is less or equal than x, plus the probability that x is less or equal than x minus epsilon, comma, xn is bigger than x. So this again is going to be less or equal than fn of x plus the probability of xn minus x is bigger than epsilon. Therefore, we have that the lim fx of minus epsilon is less or equal than the lim when n goes to infinity of fn of x. And again, this is for every epsilon positive. So now, if x is a point of continuity of f of f, then the limit when epsilon goes to 0 of epsilon positive goes to 0 of f of x plus epsilon is equal to the limit when epsilon goes to 0 positive of f x minus epsilon, and is equal to f of x. Okay, so then by a sandwich theorem, we can just say that the lim is equal to the lim is equal to the lim sub, and we have that the limits are equal to f of x. Okay, so then putting everything together, the lim when n goes to infinity of fn of x is equal to fx of x for every continuity point of continuity point x of f. Okay, so that takes care of part B. Okay. All right. Okay, so let's look now at the proof of part A. And this is a bit more complicated, so let's see if we can figure it out. So part A. So what does it mean? Xn converges to x almost surely. This means that the probability of the omegas in omega such that xn omega minus xn omega converges to x omega as n goes to infinity. But okay, but let's try to decompose this set. Let's call this set C for a second, and let's try to decompose this set a bit. Okay, so C is all the points such that xn of omega converges to x of omega. So what does it mean that xn of omega converges to x of omega? That xn of omega converges to x of omega if and only if for every epsilon positive there exists an n0 in n such that for every n bigger than n0, xn of omega minus x of omega is less than epsilon. Okay, so now what we can do is translate this into sets. Okay, so this is a set of events. So saying that omega is here, it implies that for every epsilon there exists an n0, such that for n bigger than n0 we have this property. So this is equivalent to saying that, so whenever we have a for all, this is an intersection, and whenever we have an exist, this is a union. Okay, so this is the intersection of epsilon positive of the union exist n0 equals to 0 up to infinity of for every n bigger than 0 is an intersection, n larger or equal than n0 or n larger than n0 of the omegas in omega such that xn omega minus x omega is less than epsilon. Okay, so there was, for instance, a question that I had not I had glossed over before is why is this a measurable event? Okay, why can we actually take this in the sigma algebra? And the idea is that it can be written as intersections of unions of intersections of events that we know that they're measurable, because xn and x are both random variables. This is a valid event, so we can take in countable intersections, countable unions. So what we're saying is that the probability of C, so all of this set is C. And what we are saying is the probability of C is equal to 1. So here there is, for instance, here I put epsilon positive. Here we could have put for every m. So we can exchange epsilon positive by putting little, or let's call it k, for any k in n. And here, instead of putting epsilon, we put 1 over k. And here we take the intersection over k in n. And here we put 1 over k. Okay, but regardless, it doesn't quite matter. This is how you actually make sense of this being an event. So now, in particular, what we know is that what we know is that we had written C as the intersection over all epsilons. So in particular, the set for every epsilon positive, the set n0 equals to 0, the union of the intersection of n bigger than n0 of omega in omega xn of omega minus x of omega bigger than epsilon is contained in C. Okay, so C is given by all of these intersections for different parameters of epsilon. If we fix an epsilon, then what we get is that this set is contained in C. Okay, so C was defined by the intersections of all of these guys. So in particular, if we take one for fixed epsilon, we can say that this is equal to that. So in particular, the probability of the probability that the union from n0 in n of the intersection n bigger than n0 of xn omega minus x omega is bigger than epsilon. Sorry, this is smaller than epsilon. Is equal to 1. But then what we can do here is taking complements. We obtain that the probability of the intersection of n0 in n of the union of n larger than n0 of the complement of this set, which is xn minus x bigger than epsilon, is equal to 0. But now what we're going to do is translate back into limits. Okay, so what does it mean? So taking the intersection taking the intersections here, so what we can show is that for every epsilon, this implies that the set in which there exist infinitely many n in this xn minus x bigger than epsilon has probability 0. Okay, so in particular, let's look at the probability of xn minus x bigger than epsilon. So we're taking the unions over all n0, all okay, let's try to make this easier. Okay, so now let's try to show that the limit when n goes to infinity of the probability of xn minus x bigger than epsilon is equal to 0. Okay, so then what do we do? So let's say that this is not this thing here is telling you that we can pick an x0 so this is telling you that for every delta, this thing here implies that for every delta positive, there exists n0 that depends on delta, such that the probability of the union of n larger than n0 delta of xn minus x bigger than epsilon is less than delta. But in particular, we are taking the union of all of them. We can just take a particular one, okay? So then this also implies that the probability that xn minus x bigger than epsilon is less than delta for every n larger than n0 delta. Okay, so here what we are using is the Borel-Cantelli lemma. Basically, if we have, so these are nested sequences of sets. So okay, so this is the intersection of nested sequences. So the probability is equal to 0 if and only if the limit of the probabilities of the sets inside goes to 0. Okay, so in general, for every positive delta, we can find this n0 such that this probability becomes smaller and smaller, and we actually get the desired thing, that the limit of xn minus x bigger than epsilon is equal to 0 for every epsilon positive. Okay, so in particular, we have like discarded a bunch of information to be able to go from one to another, and we'll see later on that we need actually we need to be able to get from this information to almost sure convergence. We'll need to have some summability of these sets uniformly in N. Okay. So I guess let's do the example. So example that almost sure convergence, convergence in probability does not imply convergence almost surely. And here what we're going to consider is the following. So we are going to consider a sample space to be 0, 1. And we are going to take xn, which is the indicator of a set. The indicator of a set an. So here what we can do is take xn such that the size of an goes to 0. Okay, so here we have xn. So morally what we would have is here from here to here. So let's put a1. So here we would have a1. Then H2 could be this moved to the side, A3, and so on. So the point is that we can actually make the indicator of the set become smaller and smaller. So we make AN become smaller and smaller, but we shift its position so that xn of omega does not converge to x of omega, which is equal to 0, for every omega in the 0, 1. Okay, so what I'm trying to say here is just take xn, which is an indicator here. So let's start with something simple. Let's say that x1 is the indicator of 0, 1 half. x2 is equal to the indicator of 1 half 1. x3 is going to be the indicator of 0, 1/4. x4 is the indicator of 1/4, 1 half. So x5, x6, that completes the little the 4 thingies, and then x7 is going to be the indicator of 0, 1/8, and then we're going to have 8 of them, and so on. So here the idea is that the indicator, you would have first the indicator here, then the indicator would be here, then the indicator would be here, 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 and here, and then you start again. And you start this process again. And what you can check is that this will converge in probability, because the set where xn of omega differs from 0 becomes smaller and smaller. This an is going to 0. But because we are shifting it, for every point here, we can actually check that it cannot converge point-wise to 0. Okay, so most of this introduction to convergence of probabilities of random variables will be for understanding the law of large numbers. Okay, so this is the idea is when we flip a coin a lot of times, we expect half of them to be heads. Okay, so we are going to start being a little bit more precise about what this means. So let's say that we take xi, which is a family, which is IID, and xi is Bernoulli with parameter 1/2. So the idea is to take Sn, which is the sum from I equals to 1 up to n of xi, and this is the number of heads after n flips. So what we expect is that Sn behaves like n over 2. So what the law of large numbers says says is that Sn over n converges to 1/2. And so here the question is, what is the convergence? So what is the convergence? So the weak law of large numbers convergence in probability and the strong law of large numbers is convergence in convergence almost surely. Okay, so what we saw is that the convergence almost surely is stronger than convergence in probability. So in particular, the strong law of large numbers implies the weak law of large numbers. The point is that the strong law of large numbers is a little bit more complicated to prove, and sometimes it requires a bit of extra assumptions depending on what we're trying to do. Okay, so let's start with this class. We're going to do the weak law of large numbers, and then in the next class we'll do the strong law of large numbers. Okay, so theorem, weak law of large numbers. Okay, so we take x1, x2 such that they are independent, and the expected value of xi is equal to mu for every I. Okay, so they all have the same expected value. They are independent. The expected value is equal to mu for every I, and the variance, the supremum over I of the variance of xi is less than infinity. Then Sn over n, which this is just the sum from I equals to 1 up to n of xi, converges to mu in probability. Okay, so the theorem says, so here, so a couple of remarks. One is that we don't need xi to be identically distributed. So if you have a bunch of random processes and you sum them up and you average them, you will still be hope to see their expected value in the limit, and this is independent if they are actually how they are distributed. Okay, that's one thing. And the other thing is that we do not need xi to be independent, but only non-correlated. Okay, they don't actually have to be exactly independent, but they need to be non-correlated. Okay, and the only thing that we're going to use is that we need that the variance of the sum is equal to the sum of the variance. Okay. Okay, and let's start with so a reminder, which is this is just going to be a quick application of Chebyshev's inequality. So Chebyshev's inequality says the following: the probability of x minus expected value of x is bigger than lambda is less or equal than the variance of x over lambda squared. Okay, so this is the Chebyshev's inequality which we are about to use. Okay, so let's say proof of the theorem. Okay, so let's start calculating. So the idea is to use Chebyshev's inequality. So first, we notice that the expected value of Sn over n is just equal to the sum, is 1 over n, the sum of the expected values of xi, which is just going to be equal to mu, because we are taking averages. But now the variance of Sn over n, so the variance of Sn, let's start without dividing by n, is going to be equal to the variance of x1 plus all the way to the variance of xn. But this, we're going to assume that the supremum over I of the variance of xi is equal to k, which is less than infinity. So in particular, this is less or equal than n times k. But we are not interested in the variance of Sn, but we are interested in the variance of Sn over n. But the variance is quadratic on multiplications, so in particular, this is less or equal than k over n. Okay, so here another reminder would be that the variance of ax is equal to a squared times the variance of x. Okay, and now by Chebyshev's inequality, the probability of Sn over n minus mu, which is the expected value of Sn over n, bigger than epsilon, is less or equal than the variance of Sn over n over epsilon, which is less or equal, the variance of Sn over n is k over n, and here epsilon squared times epsilon squared, which goes to 0 when n goes to infinity. Okay, so the idea is that this is a specific easy version of the law of large numbers. This is the weak law of large numbers. And so next class, we will talk about the strong law of large numbers.